So far, we have done some discussion on wave functions, some properties of physically realizable wave function, little bit about, we have done about probability density. And today we are going to come to the topic called as time independent Schrodinger equation. As you are aware that in quantum mechanics, the theme, central theme becomes the wave function itself. And we've seen that this wave function satisfies an equation which is called as the Schrodinger equation. Okay, so we've seen that this satisfies the Schrodinger equation. Apart from this, we've seen what are the properties of physically realizable wave functions. Although there are some exceptions to it, we'll see those exceptions, don't worry. But overall, we've seen properties of physically realizable wave functions. Also, we've seen something called as another associated term to psi mod whole square. Psi mod whole square represents probability density. And there is another term called as J, which is the probability current. So we have seen all these things in greater detail in previous lectures. Okay, so let us try to think that, let's say, if this equation is there, now if wave function is given to us, then we can extract the information about the potential which may give rise to such a wave function. We may extract the information about the potential also. Associated to the given wave function. So this is another part. Now you just let me just take an example and make you understand what I want to convey. So let us consider a particle of mass m, in a potential Vx, described by the wave function psi as a function of both x and t, given by a ex exponential raised to power minus iota kt minus km upon h ket x square. Here a and k are some positive constants. We want to find the form of potential. So basically, if we are supplied wave function, as I mentioned, that if I am supplied with a wave function, that is, if psi is given to me, then I can extract the information about the potential also. Let us see how. So we want to extract what? We want to extract the information, or we want to extract the form of psi of x. Okay, so we want to do this. So let us see how will I be able to do this. So I already know that this psi is given to us. Why not try doing this? So iota h ket del psi upon del t. So it will be equals to iota h ket, and del psi upon del t you can write it as minus iota ka exponential of minus iota kt minus km upon hk square hk km upon hk times x square. Okay, so if I want to write this as, this iota iota becomes, iota square becomes -1, and this minus will get dissolved, so this will be like hk here, k would also come, and then you have the psi itself because a entire this thing. So I'll write that iota hk del psi upon del t is equal to hk k times psi. Okay, now think about this. This is one thing that you should know. Now, we want to see on the right hand side, we have this minus hk square upon twice m del square psi upon del x square. So first we'll do this. First we'll try to take a one derivative. So minus hk square upon twice m del by del x of derivative of this. So this will be like a exp minus iota kt, and then minus km upon h get, I think h get from this, like, okay, so fine. And then x square is here. This thing becomes minus 2 km upon h get times x. So this is your first derivative. Now if I want to take the second derivative of the same, what I'm going to get? Minus h get square upon twice m the del by del x of this. So let me just take the first derivative for this. So I think it will be minus 2 km upon h get times x a exponential of minus iota kt minus, okay, this is one part. And another, again taking this derivative. So if I again take this derivative, what I will get? Plus, so a exponential minus iota kt minus km upon h get x square. Again take the derivative. So what we'll get? We'll get 4 k square m square h get square x square. So overall, I get a point that this particular thing, but that is that I can say as kinetic energy operator operating on the wave function would give me what? So let me write this as psi. So if I write it as psi, so I'll get h get, this 2m and 2m get cancelled, so that I'll get h get k. So here it's quite clear that if I, this h get cancels this h get, minus minus becomes plus, 2m cancels 2m, so this is h get k, and then you have the psi, and then plus psi, you have 4 k square m square upon h get square into minus of h get square upon twice m, and then this is times x square and again psi. Okay, so overall I know what is h get. On the right hand side we have iota h get del psi upon del t, and that is something that we have seen that it is equals to what? It is equals to h get k psi. On the left hand side we have, on the right hand side we have again h get psi plus, this thing is like 2 k square m, and this would be a minus, I think, minus x square. Okay, and then you have this psi, and then again vx comma t. I don't know what is the function right now, that therefore I'm writing both x and t, but late. So this gets cancelled. So we've come to know that this is not only, this is not a time dependent, not a time dependent potential. Why? Because if you just see, you can just see, if you take that there, so you'll get this, that v as a function of x only is coming, that is coming equals to 2m k square x square. So clearly the potential takes a quadratic form in this case. So basically, if wave function is given to us, then we can always explicitly find the form of the potential like we did here. So let the time-dependent wave function of the particle of mass m be given by, let's say, wave function psi of x, psi is a function of x comma t, as alpha times x e to power of minus beta x times e to power iota gamma t upon h cat for all x greater than 0, and for all x less than 0 it is given as 0. Now we want to find the form of the potential. So our interest is in to find the form of the potential, like how this Vx would be depending upon x and t or so on and so forth. And it will turn out that this potential will only depend upon x. So let us see how to approach this. So basically, we are given this time dependent wave function. So what I'll do on the left hand side, I'll use the Schrodinger equation. On the left hand side, we have iota h ket del psi upon del t, and which certainly would give me iota h ket del by del t would be what? So alpha is paired, x is paired, e to power minus beta x is paired. Now you'll have this e to power iota gamma t upon h cat, and then again you will get this e to power. So iota gamma upon h cat you get. So basically, at the end you will get h cat cancels h cat, and this uh, uh, h cat cancels h cat. Iota is iota, so minus gamma times psi. Okay, so minus gamma times psi. This is something that we are going to get here. And on the right hand side, we have minus h cat square upon twice m psi double dash, which is simply equals to minus h cat square upon twice m del by del x of the first derivative of this would be simply alpha e to power minus beta x e to power iota gamma t upon h cat, and then again minus alpha beta x e to power minus beta x e to power iota gamma t upon h cat. Okay, so this is another thing. So basically now we are going to get minus h cat square upon twice m. Now at least, now again differentiated, this would be like minus alpha beta e to power of minus beta x e to power of iota gamma t upon h cat minus alpha beta again. So this will be like 2 times, because again if you differentiate with respect to x, you will get minus alpha beta. So here you have this alpha beta, because see, exponential when differentiated will give you e to power minus beta x, and minus beta will come forward. And here again this x will get differentiated. So again in this also you have this again a term of exponential. So again you differentiate it, and this time you'll get plus alpha beta square x, right, e to power of minus beta x exponential minus iota gamma t upon h cat. Okay, this is another thing. Now we already know that alpha x e to power minus beta x e to power iota gamma t is simply our psi. So what I'll do something like this. Minus h cat square upon twice m. If I multiply x here and divide it by x, so what I will get? I will simply get minus 2. I will get beta divided by x times psi. So this is psi, isn't it? Because see, alpha x e to power minus beta x e to power iota gamma t upon h cat is psi, plus beta square will come out. Now this alpha x e to power minus beta x e to power iota gamma t is again a psi. So what am I getting at the end? So at the end I'm getting 2 cancels 2. So this is h cat square. Now this is beta divided by m times x, and you have a psi here, minus h cat square beta square divided by twice m, and then you have again psi. So overall, what am I getting? I'm getting minus gamma psi is equals to h cat square, sorry, this is h cat square beta upon m times x psi plus, sorry, again a minus, sorry, minus hk square beta square upon twice m psi plus v as a function of x times psi. So overall, from here, this, if I cancel this up, because psi cannot be zero until unless you have an infinite potential, and certainly if form of the potential is asked, so we can assume safely that potential is not infinite. So if that is the case, from here it's quite evident that v as a function of x turns out to be hk square beta square upon twice m minus of gamma. So this is some constant plus, sorry, minus hk square beta upon m times 1 over x. So overall, it's quite evident that the potential Vx would be something like constant plus constant upon x. So this is how your potential function would be of. So this is the form of the potential which may give rise to the wave function as expressed above. Okay. So having done all these things, we have already done, however, but let me just revise it for you. So what is our interest? Our interest is our prime interest is to solve the Schrodinger equation for a particular potential problem. And for most of our analysis, we'll focus on only the time independent potentials. So right now we are considering time independent potentials. Time independent potentials. Okay, now we want to see that if we want to solve this, what you can say, if we want to solve this Schrodinger equation for a particular potential, how things would turn up. So basically, one of the methods is to use the method of separation of variables. One of the methods is to use the method of separation of variables. So what we do, instead of psi, I'm just making a capital psi. So psi as a function of x and t, we write it in form of completely a function of x and completely a function of t. And when we place this in our Schrodinger equation, we get two separate equations. One equation is like this, minus hk square upon twice m, del square psi upon del x square, plus v psi is equal to e psi. This equation is called as a time independent Schrodinger equation. Please note that this e is a constant here. So basically, this is called as your time independent Schrodinger equation. Time independent Schrodinger equation. And the other term, the time dependent term, turns out to be phi is a function of t is equals to exponential minus iota e t upon h cube. This is your time dependent term. So by the method of separation of variables, when we try to solve the Schrodinger equation, we get a time independent Schrodinger equation, and we get a time dependent function which is exponentially dependent upon time. So basically, the total function can be written as the solution of this part, which will be completely x dependent, times this part, which is completely time dependent. Okay, so for most of the cases, we are going to consider potential to be time independent, and for time independent potential, this is one of the important one of the important equation that you should consider, which is called as the time independent Schrodinger equation. We can also write this you can see operator formalism, where hk is the Hamiltonian operator. Operating on psi gives you E psi. Okay. Further, this Hamiltonian operator is what? This Hamiltonian operator is simply minus hk square upon twice m, del square upon del x square right now in one dimension plus v as a function of psi. So clearly this is a time independent. Right now it is a time independent because we have not taken v having any time dependence. So this is time independent operator. Okay, so this is one thing that you should remember. Now, there are a few things that one must consider. So before moving to all those things, let us try to again think that if at all we are supplied with, let us first try to think that if at all we are supplied with a with a with a wave function which is entirely dependent upon x, can we extract the potential form? Let us see that in a little bit detail. Can we extract the potential? So this is our main query. So let us take a few instances or examples from where we can affirm this understanding. Okay, so let us do. So let us say that wave function is of the form psi x. So just take one example. I'm taking some examples in order to make you understand that if the psi as a function of x is supplied to us, then can we really extract Vx using time-independent Schrodinger equation? Time-independent Schrodinger equation. Let us see how. So we are supplied with, let us say, a wave function given by e raised to power minus of b square x square upon 2. Obviously, here a and b are some constants. And we want to so basically we want to find the potential form. We want to find the form of potential by by exploiting time independent Schrodinger equation, and for a particle of mass m, having energy E. Okay, so we want to find the form of the potential Vx, having given this psi of x. So we are given the psi of x, which is certainly some e to power minus b square x square upon 2. And we want to find what would be the form of potential Vx, which may give rise to such a potential. And let us consider that the particle is of mass m and of energy E. And let us take a few more things. Let us also take a condition. So let us consider that potential is such. Consider that potential is such that potential is 0 at x equal to 0. So this is an extra condition that we are right now taking. Having given all these things, we want to find what would be the potential form. What would be the form of the potential? Okay, so we know that this is completely x-dependent function. So what I'll do, I'll simply use time-independent Schrodinger equation, which is minus iota h square upon twice m del by del x of what will be the derivative of this? This will be a minus b square upon 2 and 2 cancels. So this is this thing minus b square x. And then you have this exponential of minus b square x square upon 2. Again, a derivative of the same minus h cat square upon twice m The derivative would be minus ab square exponential of minus of b square x square upon 2. And again, if you take the derivative of this, because the derivative of this has, I've not taken the derivative here, so I'll have to take again a derivative here. So if I take again a derivative here, so again I will get in place of a is fine. Now exponential will give me okay. So again, just recheck if there's a mistake. So a will be a common thing. The derivative will come out as 2x because minus b square x is equal to 2. This is fine. This is fine. Okay. Again, if I take the derivative, this will dissolve. That is fine. And if I take the derivative here, so exponential will remain exponential. Minus b square x will be accompanying. So this will be beta ki power 4x square. Okay, this is fine. Now, so what I'll do, okay. So basically, so now this is like h ket square minus h ket square upon twice m. You have like minus a minus b square psi plus b raised to power 4 x square psi. Okay, so this is like this is the form of like this is simply minus h ket square upon twice m del square upon del x square times basically. Okay, so what I'll do, I'll simply write this here. So this is minus h ket square, so I'll write plus h ket square b square upon twice m psi plus, sorry, minus again, minus b की power 4 h ket square upon twice m x square psi plus vx psi as a function of x is equals to what? It will give you some e times psi. Okay, we already know that at x equal to 0, potential, I have supplied you that it is simply equal to 0. So if at x equal to 0 it is 0, so this will go to 0, this will go to 0, and we'll get the total energy as h ket square b square upon twice. We'll get the total energy as h ket square b square upon twice. Now we'll use this here. So in totality, this equation now converts into h ket square b square upon twice m psi minus of h ket square b raised to power 4 upon twice m x square psi plus b as a function of x times psi is equals to h ket square b square upon twice m psi. So this cancels up, and from here we can get v as a function of x clearly as h ket square b raised to power 4 upon twice m times x square. I hope it is clear. So this is one of the important things that we can do, that if we are supplied with the potential, if we are supplied with the wave function form, then certainly what we can do, certainly we can extract the potential form. That is, we can know what potential may have given rise to such a wave function by using time independent Schrodinger equation. If the wave function is completely dependent on x, and if the wave function is dependent on x as well as on t, then we'll use simply our Schrodinger equation, which is iota h ket del psi upon del t is equals to h ket psi. Let us try to do a few more in the same few more examples, and then we'll move forward. So see, now we are just, I'm interested in the potential form. I'm just interested in the potential. Example number 2. Let me take an example again so that, okay. So now let's say the potential, that the wave function of the particle, now let me give you that the wave function of the particle of mass m moving in one-dimensional potential Vx is given by, so I'm not giving you some minus iota x plus b. Okay, and we just want to know the form of the potential. We want to know the form of the potential. We want to know the form of the potential here. So just an answer. How would we do? Simply again the same thing. I've just giving you a little bit of hint. I'm not normalizing it or anything. Just I want proportionality. Let's say I just want Vx will be proportional to what? Okay, this is what we want to do. So basically, this is equals to minus h ket square upon twice m. Now, if you twice differentiate it, if I once differentiate it, I'll get minus iota a. And if I again differentiate it, I will simply get, I hope this level of foresight I can use, because minus iota a would come forward. Again, second derivative, minus iota a again would come forward. So this would be like minus iota whole square, which is simply, so this is like something like this. Um, so this is one thing. And if I just add the potential, so this is like Vx times I, just add it up. This entire thing should be equals to what? It should be equals to constant E times psi. So if I write this as minus of A square psi plus Vx psi is equal to E psi, from here it is quite clear that V as a function of X would be simply a constant, would be simply a constant. It would be simply a constant. So Vx must be a constant. Now, if I'm supplied with some additional condition, I may be able to know that what constant is V. So in this limited hint, I can just remark that my potential would be a constant function. I hope it is clear. So such things can be done. That is, if I know that what is my, you can say, if I know that what is my wave function, then I can extract my potential. I can extract my potential. Let us say another, let me take another example to illustrate the same concept. Okay, so let us say I have some wave function of this form. Psi x is equal to e a times exponential minus x to the power 4. Okay, and let us for simplicity take that the total energy of the system is, let's say, 0. Now we want to find the form of the potential. We want to find the form of the potential. And for simplicity, consider that h ket and 2m are all equals to 1, so that you don't get bothered with all these things time and again writing all these things. Okay, so if you have this, then clearly I can do this thing. Minus h ket square upon pi m is simply 1. So this is minus del square upon del x square times psi plus v psi is equal to 0, because energy total has been given to me as 0. So that things are now at easier front. So basically it is simply that what is v times psi would be simply minus del square upon del x square times psi, and so which is so basically plus, sorry, it will be like del by del x, and the derivative of this would be minus 4 x cube a exponential of minus x to the power 4. Again take a derivative of the same. So if I again take the derivative, what I'll get? I'll get minus 12 x square a, and having taken the derivative all over again, what I will get? I will simply get 16 x raised to power 6 a. Okay. So v times psi is simply equals to minus 12 x squared times psi plus 16 x to the power 6 times psi. So from here, the form of the potential Vx is quite evident that it is something like 16x to the power 6 minus 12x squared. Okay, so it is quite evident that if we are supplied with some potential, then some wave function, then it will be easier for us to find the potential. So let me take another example. Okay. Now just consider one more thing. Consider that the energies in the ground state and excited state. I can take first excited state right now. First excited state of particle of mass 1 by 2 in a potential Vx. Okay, so consider energies in ground state and excited state of particle of mass in potential Vx as minus 4 and minus 1 respectively. Okay, and let us say that there is a relation between the first excited state wave function, that is psi 1x, and the ground state wave function, which is psi naught x, and they are related like this. Now from this given hint, we want to extract the, we want to find the ground state wave function. So just think about it. I'll start in a minute or so. Okay. So what has been given to us? It has been given to us that the ground state energy has been given to us as minus of 4, and excited state energy is given to us as minus of 1. Okay, and we know that for ground state the wave function is given by psi naught, and for excited state the wave function has been given by psi 1, which are related by this expression. And from this given hint we want to find the ground state wave function. So let us try to do this. So minus hk square upon mass is given to be equals to 1 by 2, so 2m would vanish, so it will simply remain as minus hk square. And let us use hk as simply 1 also, so that even this does not remain in the picture. Okay, just for the simplicity I'm doing it. Okay, so now this will be equals to minus del square psi naught upon del x square. Potential is given to be Vx times psi naught is equals to minus 4 times psi naught. And if I'm writing the excited state, it will be del square psi 1 upon del x square, del square psi 1 upon del x square plus Vx psi 1 is equals to simply minus of psi 1, because the total energy for the excited state is given to be minus of 1. So let me write this as equation number 1, and let's say this is your equation number 2. Now, I know that the ground state eigenfunction, wave function, and the excited state wave function are related by this expression. So I can use this here in the second equation. Okay. And let me just write it here for you. If you are not knowing what is sine hyperbolic x, it is e to the power x minus e to the power minus of x divided by 2. So if I differentiate it once, I will simply get e to the power x plus e to the power minus x upon 2, which is simply cos hyperbolic x. And if I differentiate again this, so again I will get simply sine hyperbolic x only. Okay, so having known all these things, let us start. So if I just instead of psi 1, if I'm using psi naught, sine hyperbolic x, here also v as a function of x times psi naught sine hyperbolic x is equals to minus of psi naught sine hyperbolic x. Okay, now let me solve this thing. So it will be like minus del square. So let me first do the first derivative, otherwise there could be an issue. So what I'll do, I'll take this minus d by dx here, and I'll place this inside. So this will be minus del psi naught upon del x times sine hyperbolic x, and then again this plus psi naught cos hyperbolic x plus v as a function of x times psi naught sine hyperbolic x is equals to minus of psi naught sine hyperbolic x. Again take this the derivative, that is again take this derivative. What you'll get minus of del square psi naught upon del x square, and then again this minus del psi naught upon del x. The derivative of sine hyperbolic x is simply cos hyperbolic x minus del psi naught upon del x cos hyperbolic x minus psi naught sine hyperbolic x plus Vx psi naught sine hyperbolic x is equals to minus of psi naught sine hyperbolic x. This cancels this. Okay, this cancels this. And we already know that minus this bracket I'm just making, minus del square psi naught upon del x square plus Vx some psi naught. Okay, sine hyperbolic x is also here. So what I'll do, okay, some sine hyperbolic x must be here as well, right? So I've forgotten to write this sine hyperbolic x here. So here will be sine hyperbolic x also. So if I divide sine hyperbolic x throughout, what I will get? I will simply get minus del square psi naught upon del x square minus 2 times del psi naught upon del x cot hyperbolic x plus Vx psi naught is simply equals to 0. And if I further solve it up, what I will get? So if I take this and this in one bracket, I know this is, I know that minus del square psi naught upon del x square plus Vx psi naught is simply equals to minus 4 psi naught. So entirely this entire thing would be minus 4 psi naught. So I'll write minus 4 psi naught minus 2 del psi naught upon del x cot hyperbolic x is equal to 0. And if I consider that my psi would be dependent upon x, then this partial derivative I can use as total derivative also. Okay. So, okay, so basically it was given as psi was given to be, psi naught was given to be a function of x only. So basically what I can do, I can simply write it as total derivative here. So it will be equals to what? It will be equals to 2 times psi naught is equal to d psi naught upon dx cot hyperbolic x. I think there would be a negative. Okay, so there would be a negative here, and which is simply equals to minus 2 tan hyperbolic x psi naught is equal to d psi naught upon dx. Now, what I can do, I can integrate on both sides. I can integrate on both sides. So basically, so on del x is equals to minus 2 tan hyperbolic x dx integration. Okay, now let us integrate this up. So on the left hand, like this is what I'll write it as minus 2. What is tan hyperbolic? It is sine hyperbolic upon cos hyperbolic, right? So if I take this as t, this will be simply dt. So this is minus 2 dt upon t, and this is simply integral of d psi naught upon psi naught, which is simply log psi naught. So I'll write ln psi naught on the left hand side equal to minus 2 ln of t, right? And some obviously some constant as well. So I'm not bothered about the constant. I'm just bothered about the wave function form. So this will be minus ln psi naught is equals to ln of t raised to power minus 2, which is like, what is t? It is ex plus, so I'll simply write it as e power x plus e power minus x minus 2. And what I can do, I can divide it by 2 and further take this in a constant form only. So I'll take this as ln k. So basically this 2 which I have supplied here, I'll take as a constant here. So basically what it is equals to ln psi naught is equal to ln of cos hyperbolic x raised to power minus 2 plus ln k1, which implies that my wave function, the ground state wave function, would be of the form The ground state wave function would be of the form of sec hyperbolic square x. Some constant would appear, but I'm not interested in that. I'm interested in the form of the wave function. So the form of the wave function would be dependent upon sec hyperbolic square x. So having done all these examples, let us do one more example. Okay. So given that h ket is equals to 1 and m also is equal to 1. Okay. We want to find the potential which may give rise to a wave function of the form. So I'm not using the normalization constant here, of the form exponential minus of x square upon 2 cos hyperbolic root over 2x. So we want to find the form of the potential, and we are given with the wave function. Okay. So how to go about this problem? So we are given the wave function. It is unnormalized. So basically, I'm not interested in normalizing it right now because I just want to find the form of the potential. Okay. I'm just interested in finding the form of the potential. So if I take the first derivative would be equals to what? Exponential of minus of x square upon 2 times minus of x and cos hyperbolic root over 2x plus exponential of minus of x square upon 2 times root 2 sine hyperbolic root 2 x. Okay. Now, if I want to take the second derivative would be simply equals to exponential minus x square upon 2 x square cos hyperbolic root 2x minus exponential of minus of x square upon 2 cos hyperbolic root 2x minus root 2x exponential of minus of x square upon 2 sine hyperbolic root 2x. Again, there would be the derivative of this, so sine hyperbolic thing. So plus so we have done the derivative of this thing. So this has come as this. We have done the derivative of this. This is fine. We have done the derivative of this. This is fine. We have to do the derivative of this also, right? So this will be like exponential minus x square upon 2, and we'll get minus of x and root 2 sine hyperbolic root 2x, and again take a derivative. Oh, these are many derivatives altogether. Okay, fine. So this will be exponential of minus of x square upon 2, and then this is root 2 will becomes 2 sine cos. So cos hyperbolic root 2x. So it's a big deal. Okay. And for simplicity, we've already taken that h cat and m are already equals to 1. So that way, at least we've simplified our life. Now let us take something common out and put it in one form. So exponential we can take common out. And inside we'll have this x square cos hyperbolic root 2x. Okay. This here we have 2, here we have 1. So I think this would be plus just take this. This is fine. So this we have seen, this we have taken. Now just consider this. And here you have this term. So what I'll do, I'll write it once at least. So basically what I'm doing, I'm trying to put things in whatever e की power minus x square upon 2 is common. So I've taken that common. Now I'm just trying to write off the remaining term. So in the bracket, I will simply have cos hyperbolic root 2x. And then there is a bracket here as well. So minus root 2x is here. Minus root 2x is here. So minus, I think I should write 2 root 2x. Okay, so this is side of a dash. So I know this minus of h cat square upon y is uh, minus of h cat square upon twice m. So okay, m we have taken 1. So this is I think minus of half exponential of x square cos hyperbolic root 2x plus cos hyperbolic root 2x minus 2 root 2x sine hyperbolic root 2x plus vx psi. We want to find this form of the wave function here, and is equals to e psi. Okay. Now here, if I just take cos hyperbolic root 2x common, so I'll simply get minus 1 upon 2 minus of 1 upon 2 exponential of minus of x square upon 2 times cos hyperbolic root 2x. If I take this common out, so I'm going to get x square plus 1 minus of 2 root 2 x tan hyperbolic root 2x plus vx times minus exponential of minus of x square upon 2 times cos hyperbolic root 2x is equals to e exponential of minus x square upon 2 times cos hyperbolic root 2x. Okay, so this is one thing. Now, further, I can take this all commons, like I can cancel them up, and I want to find the form of the potential. So the form of the potential Vx, the form of the potential Vx would be simply E plus half plus x square by 2 minus root over 2 times x tan hyperbolic root 2x. Remember, addition of a constant and subtraction of a constant is not going to change the form of the potential. So if I'm adding a constant and if I'm subtracting a constant from the potential form, it is not going to create any impact on the overall potential. So Vx, I can conveniently write it as equivalent to x square upon 2 minus root 2x tan hyperbolic root 2x. So in general, I can prove